Exciting.
Hey guys, thanks for joining. We're going to give it a couple minutes for the rest of the people to filter in here, um, and then we'll get started here in a couple minutes.
This would be a very interesting topic.
Yeah, thanks for doing this, Paul. We really appreciate it.
Yeah, not a problem. I think that was a good fit to have you guys look at some of the smaller hot runner systems that we offered.
Yeah, when we run at the NP show, that was very good.
Yeah, certainly we have a lot of customers asking us which, hot runner solutions and what can we do, even though it may be micro or micro adjacent, how can we save material? It comes up all the time. So, I think we've got a good, hopefully some good questions, and it looks like a good turnout. So,
yeah, I like the case studies that you're going to show. I think people love to see real case studies, so very beneficial.
Yes.
Yeah,
give it another minute here to get started.
Okay.
Yes.
That's good.
One.
Okay. All right. I'll get started with introductions here. I will just start off by thanking everyone for joining. My name is John McNamara, technical sales here for Sodick injection molding for about 3 years now. We're joined here by Bennett Howard, another technical sales, and Bryce Maxwell with another technical sales, and then obviously our Vice President Kohei Shinohara is here as well. We're hosting Paul Botker from Technoject Machinery to discuss his Heitec hot runner systems. The way this webinar will work today is Paul will have about a 40, 45-minute presentation. And then at the end, we'll go into a Q&A portion. You'll see a Q&A tab at the top of your screen where you can type those questions in. And at the end, I will go through and read those questions to Paul so he can help answer your questions. The Sodick and Friends platform has been a great series for us. This is the Sodick and Friends webinar platform, and we do take this series sort of on the road to at various open houses around the country as well. So we look forward to seeing some of you guys at those in the future also. To introduce Paul, I will go into it here. Paul is a longtime technical sales professional with significant experience and expertise in the field of hot runner systems and injection molding equipment. He has a passion for helping customers find better solutions to their hot runner needs. With over 35 years of experience in the injection molding industry, Paul specializes in developing innovative hot runner applications for challenging mold requirements. Without further ado, we'll get going with Paul. Or Kohei, have something to say? Go ahead.
Yes. So Paul and I had some collaboration at the trade show in the past and mutual customer. So this is a very good opportunity to introduce him to his own very unique, very beneficial technology. My passion is micro molding, and the lot of things that he's gonna talk about is related to my passion too. And this webinar will be recorded, and we're going to publish in our YouTube channel. So check out later, or you can share with your colleague after this webinar. And please follow our LinkedIn and our YouTube. We will put the more technical information there. So please follow us. Thank you.
Thanks, Koei. All right. Well, Paul, I'll hand it over to you. You can get started and share your presentation, and we'll go from there.
Hey, John and Kohai, thanks for the introduction, and thank you for inviting me to your Sodick and Friends webinar series. And I'm excited to present to you the topic of today: unlocking innovation with high-tech hot runner systems and compact solutions. Just a quick service announcement for, I looked at the list of participants already, and it looks like a good variety from the East Coast and West Coast. So we still had snow yesterday. So I envy you guys on the West Coast, and hopefully you can send us some of that warm weather to us. But before I dive into the topic, just wanted to give you a quick background on the company's journey at Heitec. The Heitec system was founded in 1987 with a strict focus on making things more compact and more efficient with regard to mold designs. So over the years, we evolved, and we still have our focus on that compact design, and we'll talk about some of those topics today in the webinar. So some of the topics that we look at is compact systems, close spacing layouts, new small size edge gate designs, and so to look at a typical hot runner concept that Heitec has been using over the years. At first glance, it doesn't look like anything out of the ordinary. It's a fairly general design that you would come to expect from a hot runner system. And the typical key points here are external heating. It has thermal isolation and profile heating. And in our case, it's corrosion resistant also. So typically, in the old days, the molder or designer would stay away from direct gates that are less than 1 gram of part weight. And you can see some of the the smaller type sizes get really small. They look big on the screen, but if you actually have it in front of you, then they're quite tiny. So I'm just going to run through some quick examples without much explanation because we're going to go through some of the concepts later. But here you can see these are all direct gate type applications in different materials that were done with our hot tip or valve gate type system. And so there's a range of materials that we've done in the past. So not only the commodity resins, but engineering resins also that typically have smaller processing windows. So we found that especially in the medical electronics industry, there's a good need for making things more compact because they do have a large variety of small size parts that they would like to directly gate. So how do we get to that point? We like to look at three items or three-pronged approach to come up with designs that make things more compact. So the first thing we look at is nozzle sizes, where we can look at nozzle length and diameter also. A compact layout will also make things more compact with close drop spacing, and the thermal transfer is also important to be able to still transfer enough heat even in a small size design. And why we're looking at all of that, a lot of it comes down to residence time. And especially when you look at engineering time residence time becomes very critical. So if you're looking at a part that's only half a gram or so, you cannot afford to keep the material in the system for 40 or 50 shots. So let's take a quick look at the general design of our nozzles and how it's beneficial to small type applications. With this type of design, we look at a flow channel that has, most importantly, a heater coil that's metallically bonded to the flow tube. And the metallic bonding increases the heat transfer efficiency quite a bit. So by doing so, you need less wattage to actually transfer the same amount of heat compared with like a larger heater band. So with the metallic bonding, we can transfer the heat quite efficiently down into the tip area. We also have a separate casing around it that additionally insulates from the cold cavity. So that allows us to bring the nozzle sizes down. This nozzle that you see here has an overall length of 35 millimeters, or somewhere around 1.3/8 inches. And again, with this nozzle here, the heater would be metallically bonded on the inside to provide a good amount of heat for even running nylon 6/6 materials with good results. So jumping into some case studies, this is a typical small part. It's called a small bearing cage, and it's used in the automotive sensor industry. And you can see that this part only weighs 0.015 grams. If you look at it in your hand, you probably think that it's like a pellet. But regardless, this part is directly gated, so the number of shots in the system is important because you don't want to overheat the material with having it in the system for too long. So how do we get there? We have a compact round manifold that can keep 6 nozzles like this on a really very small mold circle. So the advantage of doing it this way is that you don't need a large rectangular manifold block to convey the material to each drop. And the drops themselves are quite small also. They only have a 13 millimeter bore and a 3 millimeter flow channel. So the material goes through there quite quickly. But the customer was also saying, well, I want a direct gate with individual control over each gate. So this nozzle setup is the ideal because you have 6 separate heaters controlling each gate with thermocouples. Because a lot of people would say, well, you can get multi-tip nozzles that do the same thing. With multi-tip nozzles, you do not have the individual control over each gate. So here's just a quick section that you see of a round manifold where you can see the streamlined flow channel leading down to each drop. So the material is getting through there quite quickly. And you can also see the flow channels in the manifold are tailored quite small to get to that to get to the drops. And then from here with the drops, you can choose different lengths to suit your mold design. So all of this talk about compact design wouldn't be complete without talking about our what people know us for is our flat nozzles. And we had these flat nozzles introduced already back in, I think it's around the year 2000. So this nozzle has been around for a long time. And as far as I know, Heitec are the only ones that provide that kind of flat nozzle. And you ask yourself, why have a flat nozzle like that? And we'll go into some examples of why this could be quite useful. With this type of flat nozzle, you can achieve a minimum drop spacing of 4.5 millimeters. So that opens up a whole new range of articles that can be molded with this type of nozzle. And not only can they be spaced close together, but they're also suitable for engineering type resins. And as with many of these nozzle designs and product introductions, oftentimes they come out of a need that the customer has and comes to us and says, hey, can you build something that will do this and that without having to change my original objective? Well, the original objective with this customer was to place a gate on each of these LEDs overmold on a reel-to-reel type application. So with a reel-to-reel, you basically have 2 big reels on beside the molding machine, one to unwind and one to wind up on the other side. And it runs indexes through the mold, and you overmold a plastic part on the metal strip itself. So in this case, the part spacing was only 7 millimeters, and the customer had an existing multi-tip design that did not give him good results because of not being able to. So with that in mind, he came up with a flat nozzle that would give him that spacing, and they were able to have an individual gate on each part. And then from there on, a whole bunch of new applications opened up and were used with the flat nozzle design. So we did, for example, a toothpick arrangement that is connected in between the various toothpicks for easy packaging. And so this spacing between the toothpicks is only 4.5 millimeters. And we built a demo mold to mold these. that we use in-house and customers can try out for different materials. As a matter of fact, we had this mold running at the NPE in 2018, and we asked Sodick at the time to provide us with a demo machine so we can run it in our booth. And it was a really good demonstration of our capabilities, and as well as the Sodick machine was also performing really well on this. So, as an interesting sideline, I asked Kohai at the show, and if you've been to these shows and exhibited there, there are some times where you do have more time and it's less busy. And so I asked Kohai, well, can you show us how precise these machines are? And so he said, okay, well, you have these toothpicks. We can reduce the fill size and progressively fill less. So he did that in very short increments, and with every shot, all the parts filled slightly less. We always took away 3-4%, and we're able to get it all the way back there to a consistent fill across.
Yeah, we should keep the sample 90% fill, 95% fill, 99% fill. You should collect those case studies.
To me, that was quite impressive because with the small part weights, you don't have much room to play in terms of injection. When the material flows through the hot runner for these small part sizes, it only moves like a tiny bit every time. And to have that control over it, that was quite impressive. So yeah, we're quite happy with that setup at the show. And just to jump through a couple of different applications, you can see 4 drops here in a row that would mold these little these nylon 12 gears with a direct gate of only 0.6 millimeter, 24 thou, with a 7 millimeter spacing. So if you can look at this compact design, you can run this in a very small machine. You could run this, for example, in a 10 or 20 ton machine, no problem. And you can save on space, and most importantly, you can overcome the challenges of residence time that, especially with like a nylon 12, where the processing window is quite small. Sometimes you may only have 20 or 30 Fahrenheit of window where you can process these resins. One of the more popular applications are these cuvettes and medical parts that require a close spacing, because it's basically, if you look at it, it's one part. But in this case, it has 9 compartments, and they use these cuvettes for inserting it into a machine and shining a light through it and do their analysis. Not 100% sure how it exactly works, but I was told that these windows are very important and need to be perfectly clear without any flaws. So the best way to mold these is to have a gate on each compartment, because then the knit lines between each gate happen to be in between the compartments where it's not as critical. And it also, by having the gate at the top, it drives the air out to the bottom, and you don't have to worry about air traps. If and I've seen these also, you put only 2 gates on this, only 1 gate, you can still fill it, but oftentimes you end up with a knit line on the cosmetic part here, and oftentimes you would also get air traps, and it becomes a lot more challenging to mold that way. And so that development of the hot tip designs, like I said, was about 25 years ago in the year 2000. And I would say, I would leave it up to the medical industry to ask for valve gates. So, of course, we had to come out with a valve gate. And these valve gate nozzles have a similar concept and shape as the hot tip designs, and with a slightly bigger drop spacing. So here you need a minimum of 5.8 millimeters drop spacing for individually heated and controlled nozzles. So when the medical industry realized that this type of spacing is available valve gates, it opened up a whole new set of applications that we were able to do successfully. So, the biggest and most popular application is many nozzles in a row to gate onto a cuvette or a vial strip, PCR tubes. There's a whole range of diagnostic pieces that require those kind of valve gate styles. Again, all these heaters are still run with 230 volts, so you don't need any special temperature controllers, although we do supply temperature controllers that are quite sensitive to the smaller size heaters. Now you ask yourself, well, how do you balance something that's that close on a row? And so we came up with the balancing that is done in one level here with the rounded corners, and so the manifold is designed in 2 pieces. You would have a bottom and a top piece in 2 halves, and you would mill the channels in between the 2 halves to come up with this balancing pattern. And then the 2 halves are fused together. They basically form a metallic bond. It's quite interesting how they do that. And they're capable of withstanding a good amount of pressure to stay together. So with those designs, you can be quite creative in the balancing, and so you can design these to suit your needs. This would not be possible with the conventional drilled and plugged manifolds that you're all familiar with. So to continue with the valve gates on the medical applications, we do a lot of these cuvettes. In this case, it's a 5.8 millimeter spacing in acrylic, and in this case, it's an 8-cavity mold with 10 nozzles on each part. So you're looking at 80 nozzles plus manifolds because it has like a couple of layers of manifolds. So it becomes quite a complex system. But the alternative for the customer would be to go with a cold runner application that would not be suitable for efficient molding. especially with all the waste and possible particulates that might break off and end up on the surfaces. So if you look at the valve pins being so close together, we had to come up with a mechanical actuation that drives these pins together, because you could not have individual pistons driving these valve pins. So a mechanical actuation relies on the cam system that engages the cam rod with the needle holders. And then out here, which is on the side of the mold, you could then have a pneumatic, hydraulic, or preferably a electric motor that would drive these valve pins in synchronization there. Here's an example of a cam system driving all these valve pins together. So when you do choose servo motors for the linear motion, we can stack those on top of the mold, and they would drive the various cam bars depending on how many you have. Oftentimes you only need one of those motors. And then it comes with a Visio controller that controls the actions of the servo motor with many features such as a force limiter, you can automatically adjust the position of the valve pins, the speed of the valve pins, and you can even change the travel profile. So, for example, you could have the valve pins travel very fast until they reach the gate, and then you slow down the valve pin speed to enter into the gate orifice. That would prolong the life of the gate orifice and the valve pin. And you can adjust closing and opening. For example, you can delay the opening with the valve pin controller. So if you wanted to build up a little bit of pressure inside the hot runner and then open after you build up a little pressure to have a faster, more even fill, those are all the kind of processing you can adjust with the valve pin controller. So there can be a complete family of components that work together, from the temperature controller with touchscreens to valve pin controllers, the hot half itself, and of course the molding machine, all working together and communicating together also. So coming back to the initial reason why these flat nozzles were developed in the first place is for the reel-to-reel applications. And one of the more recent applications we've done was with valve gates, and having a direct gate on each compartment. In this case, the spacing is 8 millimeters. And you can see how the reel runs through the mold, and it indexes for 8 pieces. And then you have 8 valve gate nozzles that gate on each part. The parts also have 30% glass fill. So we come to that later for how that affects it. But in this case, you can see an 8 mm spacing, and we added a couple of dummy nozzles on the side. And the dummy nozzles we put in to make sure that the fill is even all across. Here's a fill study of the system without dummy nozzles. So the outer gate does not see as much heat, or the outer nozzle loses a bit more heat than the inner ones. So we added dummy nozzles to provide heat on the outside also, and the fill is even across all 8 nozzles. That was the reason for adding these dummy nozzles. And to come back to the 30% glass, we added a small gate bushing on those small nozzles, so that if you do see some wear on these valve pins over time, those gate bushings can easily be replaced. And that diameter of gate bushing is only 3 mm, so it's about 1/8 of an inch. So you don't have a huge gate bushing to deal with, especially if the part is very small. Then you can place a 3 mm gate bushing on there. Again, this is a cam system. So we have the cams interacting with the needle holders. Because of the cam systems being in mechanical actuation here, the offset from the center was only about 3/4 of an inch, which is quite small for a valve gate. The problem is always the screw in the center. So by having a cam system like that offset, we can keep the row quite close to the center, which helps to keep the mold base small and helps to keep the machine size relatively small also. One thing that when we talk about compact systems, we can't forget is stack ups. And oftentimes with valve gate systems, the companies can supply a hot runner system that has relatively good spacing between the drops, but then there's a long sprue at the back to accommodate big pistons and big plates. So we came up with a small pneumatic cam system that allows us to have a hot half height of only about 4¼ inches. So that becomes quite useful for the mold designer that always says, "Hey, I'm running out of mold height. Can you spare a few more inches?" We hear that almost on a weekly basis. So with this type of design, you can get a couple more inches to have enough height for your mold design. And we can, with this type of design, we can have mold base sizes of as little as 5 or 6 inches with a fully operating pneumatic valve gate and a manifold. In this case, we have a hot half height that's only 4.1 inches, runs in a 15-ton machine with 40% glass. So I just want to jump over to edge gate type designs, which is something that's becoming a lot more popular these days. And just to give you a bit of a history on the edge gates, if you're old enough like me to remember the old hot edge gate nozzles that had a cold slug, they were a real pain to run. They were terrible because you always had to deal with the cold slug that you had to push out into the part. So with the new hot edge gate systems that are on the market, the tip can go all the way to the part surface, and the processing is much better because you don't have a 20 thou cold slot that you have to force out into the part. So with this design, you can see here the tip goes all the way to the part surface for gating these caps. And our edge gate design is in a way where up here it's actually quite skinny, and it allows you to put additional fit features in the cavity side. One of the big advantages of our edge gate is that you do not have to split your cavity block. So with this design, you can keep it as one piece. It's more robust. The cooling is a lot more efficient that way. And you also don't have to worry about small little pieces that you have to add to assemble the unit. So with that in mind, packaging is always a high cavitation type industry. We do, for example, a spray bottle cap in 64 cavities that has no subrunners. It comes out directly as a finished part with a good fill. This linear type edge gate system has a 4 channels that go directly to each tip, so it's fully balanced that way. And of course, it comes in round versions too, also another 64 cavity, making these small little pieces for the medical industry. Tips are available as angled versions also. And so you can have different shapes like this, or adding a 45-degree surface, for example. Last year we came out with a mini edge gate, we call it, or a Starline Crown Mini, which has a much shorter height, so you can use it again in smaller machines, but still getting an 8-cavity type system out of it. And you can see the length from the tip back to the shoulder is only 24.5 or less than an inch. Full circle would be 56 millimeter. And using the Starline Crown Mini, you can create a 64 cavity for small parts that are not that tall. You can see that that part is not very tall. So in terms of stack up, it doesn't take up much room at all. So just a couple other examples of short stack up edge gates. These edge gates can be used as stack molds also. And now a lot of times people ask me, well, how do you disassemble these edge gate systems, because the tip goes like right into the cavity. So we put together a quick demonstration on how these things come apart. And so the piece at the back, the snorkel, separates quite easily from the crowns, the front portion. And the actual crown with the tips stays in the cavity plate. And you would remove the wires from the crown to disconnect the wires without having to disconnect the wires from the plug. And then you would disassemble the tips from the front with a tool set that we supply. And those tips actually come out fairly easily with our special tools by first removing the spacer in between the tips, and then removing the tips with that tool. So the tips slide to the middle and then slide out through the parting line. And that is the method for getting the tips out without having to split the cavity block. So our system is very robust that way, and offers numerous advantages in adding cooling and having more steel available. So then the screws come out that hold the crowns from the back, and then the crowns are pulled out from the front. So it becomes a very simple process, and can be done on site by the customer themselves. So yeah, Kohai, I'm not sure. I have some more custom slides we can go through, but I'm not sure how we're doing on timing here.
Hey,
If you
Paul, yeah,
wanted
you can keep going a little bit more if you'd like. If you have some more things you want to touch on, and we can get Q&A going in a minute or two. But if you got more things you want to touch on, go ahead.
Yeah, maybe the last thing I would jump into quickly is our new introduction of the Primo line. That we always get asked, can you bring out a nozzle that is relatively low cost and still has very good profiles and heat transfer and can run the engineering resins that I would like to run. So with this Primo line, he came out with a design that has excellent heat transfer all the way down to the tip, and can be had from stock relatively quickly, but also run engineering resins and with relatively low cost. So that's always the question that comes up is, do you have a nozzle that can run polypropylenes as well as the peaks at the 750 Fahrenheit? And with this nozzle, you can do it, have very good thermal profile in the tip area, and still run this at a low cost to the overall mold. Yeah, so that's basically all I wanted to still come up, and you can see all these components are easily replaceable on site, and both in hot tip and valve gates. So I
Right.
think from that point of view, I think it's best to just hand it over back to you and see where you want to go from there.
Yeah, thanks, Paul. Really good job. That was very interesting. We have a couple questions coming in here now, and if you guys have any questions, feel free to submit them in the Q&A tab that you see at the top of your screen. But I'll get started here with a couple questions that have already come in. First one, good question. Have you established a turnover rate by material type you try to stay within?
A turnover in terms of what flow rate per nozzle, how much volume you can get through the nozzle per material and part weight. I think that's what the
Yeah, I
question
think
is,
so too.
or is it more of how long does the nozzle last in terms of how much material we can get through over so many shots?
Yeah,
So yeah,
volume.
so we do have parts that establish the type of nozzle that you can choose based on part material and part weight. We also have to look at flow lengths inside inside the cavity, which makes a difference on how fast the injection is and so on.
Thank you. I got another good one here. What are the injection pressures limits for these small nozzles? We run engineering resins that usually require high pressure capacity.
That depends on the nozzles. Obviously, the smaller you go, the less pressure it can handle. But we've done, actually just recently, we've done nozzles that can reach up to like 34,000 PSI. And we typically like to use our round nozzle that is a bit more robust that I described in the beginning. So depending on the application, we can go up to 34,000 PSI. We've done those in the past. But on average, the systems, I believe, only go up to about 26 to 28,000 PSI for the average type nozzle. And then after that, we have to look at maybe we need to choose a certain round nozzle that can handle that higher pressure.
Got it. Thanks for that. Okay, here's another one. How does an edge gate affect the flow of material up against the part surface?
Well, we like to, maybe I could pull up
Yeah, feel free.
some slide that I haven't gone into detail there. So typically we recommend to have the gates at 90 degrees to the part surface, because when the mold opens and the part comes out, you want to have a nice sharp edge to shear off any sort of remnants that might be still in the gate area. So 90 degrees is ideal, and we also recommend a certain height in this area of plastic that you should have above the gate to get a good shear. We've had some customers that deviated from that. We've seen like 5 degrees or 10 degrees, and we always say, it depends on the material and how that shears, but we've had some good success with some gates that are on a 70-degree angle or 80-degree surface as opposed to the 90-degree surface.
Okay, good. Thank you for that. I got a couple more here. Do you offer sequential valve gating for relatively small parts within thin walls?
Yes, there's a couple of ways we can do this. Obviously, we can stack several servo motors in line to get sequential valve gating, but sometimes that assumes that the customer or the mold design has that space to be able to space them that close together. We have other applications where we actually stagger the valve pins with individual pistons, like round pistons, similar to, let's see if I can find it, similar to this, but just with a single pin as opposed to 4 pins. And then so if you have another gate that you would have sequentially open and close right beside it, you would actually have a second piston in a second plate on top of it. So you basically have 2 actuation plates on top of each other, and that's how we can get the sequential opening and closing by having separate airlines.
All right. A couple more that have been flowing in. Thank you guys for asking the questions. So here's a good one. The part volume is very small, which results in relatively long residence time in the hot runner system. Given the extended residence time, how can this be effectively managed to minimize material degradation?
Well, yeah, that's a good question. Thank you. Coming back to perhaps a layout we had earlier. There's a couple of things we could do, and we always do. Obviously, we calculate residence time in a system like that. But you can see how the flow channels are getting progressively smaller as it reaches the gate. And it's very streamlined. So if you would compare this to, let's say, a couple of stacks of manifolds on top of each other just to get the balancing, you would increase the residence time quite significantly. So we look at the layout in the manifold. The other thing we look at is the stack up. So we purposely make the stack up of the valve gate hot half quite small so that the material that flows through the manifold and the screws is very short. And that way we can address residence time by taking some of that flow distance out. So we can significantly reduce the residence time if you compare it to, let's say, a valve gate system where the nozzles are 2 inches apart, and you have a long connecting sprue that's like 6 inches long or something like that. That would oftentimes throw out the whole project because the residence time would be something like 30 or 40 minutes for an engineering resin, and that wouldn't be possible. So we look at this very carefully to make sure that we can stay usually under 10 minutes or so in terms of residence time. And of course, as I mentioned earlier, the flow channels of these nozzles are quite small. This particular nozzle only has a 2.5 millimeter flow channel. So you can imagine that material flows through there very quickly and only has maybe, in this case, maybe like 2 or 3 shots in the nozzle.
Very good. Very interesting. We have a couple more here. We've got a couple minutes left for some more
Sure.
questions. So do you have any recommended mold makers? Any difference with conventional molds?
In terms of like recommending mold makers, I'm sure I can provide a list of mold makers that we had good success with. And I wouldn't want to share it here, but if you reach out to me, I can definitely do some recommendations. But we find that especially on the higher cavitation applications, you want to have somebody that has repeatable inserts and can pay attention to the the sealing bores and the installation. So going back to those small nozzles, let's see if I can find a good example. These nozzles here, you see that titanium ring that seals off in the bores, and it's fairly, small nozzle bore that you have to reach down into. And we always recommend that this bore is ground to have a good seal. And so the mold maker has to have that capability to reach down into a small opening like that and put on a ground finish as opposed to just an EDM finish. And we run into this often where the customer says, "Okay, well, I can't reach down in there," but it's important that you reach into that bore and get a good ground surface. So typically, the more experienced, established mold makers can finish those no problem.
Okay, and I think we'll have one more here, and we'll wrap it up. Do you have any weakness by having a small manifold?
Weakness in terms of stability. I think you have to look at it in terms of relation with a molding machine. If you're only having a 15-ton or 10-ton molding machine, or even 20-ton, a very small manifold does not make a difference because the whole injection pressure can be high, but you're looking at small parts, so you don't have any projected forces that can really push on those plates. You have like tiny surfaces, and so yeah, you can generate higher pressures, but the overall force on the plates is relatively small because of the small size parts.
All right. Well, thanks, Paul. That was very informative. I think you did a great job. And we thank all of you for joining us as well. We would love to have you join us for our next ones. So stay tuned to social media, and we'll be posting about some of the next upcoming Sodick and Friends. We have about 5 or 6 people that are in the hopper that we just have to schedule. So we'll get that scheduled, and we'll be in touch to let you know when the next one is. And we'd love to see you.
Well, thank you very much also for inviting me again, and it was a great time with you guys.
Thank you. Koei, I think if you have anything to say, you're muted still, but.
No, thank you very much for everybody to join it. And thank you, Paul. That was very, very educational, informative. Thank you.
All right.
All right.
Thank you very much.
Thanks, guys.
All right.
Bye-bye.
Bye.
Bye. Well, thanks, Kawhi. I hope it worked out good. Your members got some information out of this.
Thank you.
Yeah.
Yeah, that's very good. Thank you. Have a nice day.
All right. Thanks. Bye.